Hi, today we're going to start focusing on binomial expansions. What's a binomial? A binomial is an algebraic expression with two terms. So for example, a plus b is a binomial. If I raise that quantity to the first power, I just get a plus b, obviously. If I raise it to the second power, we get a squared plus 2ab plus b squared. Now remember, when you're working these out, you're actually multiplying a plus b times a plus b. We're not just squaring the a and squaring the b. That's not what this means. That's why we have the parentheses. So we have to distribute, i.e., you probably heard the term FOIL. And so we have to multiply each term in the first expression with each term in the second expression. And we get 4 sets of multiplications, and then we combine like terms to get the 2ab in the middle. When we raise it to the third power, we get a cubed plus 3a squared b plus 3ab squared plus b cubed. And if I do it one more time to the fourth power, we're going to wind up with that expression. Now, if you notice, there's a lot of things going on with patterns here. So first of all, when we raise it to the second power, notice we have a to the second, then we have a to the first, and then we have a to the 0, which is just 1. And then the b's, we have b to the 0 to start, which is 1, then b to the first, then b to the second. So we're listing all the possible combinations. So when we raise it to the third power, we have an a cubed, then an a squared, then an a to the first, and then we have no a term, which is like a to the 0. And then b is in the opposite direction. We don't have a b term, or we can think of it as b to the 0, and then b to the first, b to the second, b to the third. So the pattern with the variables is pretty easy to list out. So even if I asked you to do a plus b to the fifth, I think you could list all the variables with all the proper exponents. But the second question is, how do we know what numbers go in front of each term? So here it was a 1, and then a 2, and then a 1. Here we have a 1, and then a 3, another 3, and then a 1. On this one we have a 1, and then a 4, and then a 6, and then a 4, and then a 1. So is there a pattern here? Well, a mathematician by the name of Pascal did some work with these and recognized that as we keep going, these coefficients make a triangle, and it's called Pascal's triangle. And so here's the first several layers or levels of Pascal's triangle. And here's what we do. So we start with a 1 at the top, and then we have 1 on the diagonals to the left and to the right. And then, to get the numbers in between those ones, we look at the two numbers that are above it. So for example, 1 plus 1 equals 2. For the next level, 1 plus 2 equals 3. 2 plus 1 equals 3. Keep going. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And so on and so on. 1 plus 4 is 5. 4 plus 6 is 10, 6 plus 4 is 10, and 4 plus 1 is 5. So if we wanted to do the next level, we'd put 1s on the outsides, and then we'd look at 1 plus 5, and that would give us 6. And then 5 plus 10 would be 15, and 10 plus 10 would be 20, and 10 plus 5 is 15, and 5 plus 1 is 6. So these numbers are giving us the coefficients when we're taking a binomial and raising it to a power. So if I do a plus b to the 0 power, it's 1. And that matches up with there. And then if we do a plus b to the first, the coefficients of a and b are both 1. When we do a plus b squared, our coefficients are 1, 2, and 1, which we saw right up here, 1, 2, and 1, and so on. So Pascal's triangle helps us fill in what the coefficients are for raising a binomial to different powers. And then this one here would be this last row, would be a plus b to the sixth. And so on and so on and so on. In the next lesson, we'll learn about the binomial theorem, which gives us another way to calculate these coefficients. But for now, we'll just use Pascal's triangle. And so what I did here is I expanded out all the different powers up to a plus b to the fifth power. And in red, you can see those numbers that make up Pascal's triangle. All right, let's try a couple of examples. I want to expand 2x plus 3y to the third power. Now what I want you to remember is you have to think of a plus b to a power, but the a is really going to be 2x, and the b is going to be 3y. So from Pascal's triangle, I remember that we have a 1, a 3, a 3, and a 1. Let me go back over to that. We're referring to this one right here. We had a 1, and a 3, and a 3, and a 1. Okay, so now what we have to do is we have to take our a to the third power. Well, a was 2x to the third power. And then b to the 0 power, which is just 1. And then the next term, I'll have the a, this time only to the second power, and the b to the first power. And then for the next term, we'll have the a only to the first power, and the b to the second power. And then for the last term, we'll have a to the 0 power, which is 1, so I don't really need to write it, and then b, which is 3y, to the third power. So let me write underneath here so you know where this is coming from. So it's 1a to the third plus 3a squared b plus 3ab squared plus 1b to the third power. And I just replaced the a and the b with the 2x and the 3y. And so now what I need to do is just simplify. So 2 to the third power would give me 8. So I'm going to have 8x cubed. For the next one, I have 3 times, now the 2 squared is 4. So I have 3 times 4 times 3. So that'll give me 36. And then I'll have x to the second power, y to the first. For the next term, I'm squaring the 3, so that'll be a 9. So I have a 3 times 2 times 9. That's 54. And then x to the first power, y to the second power. And finally, I have 3 to the third power, which is 27, y to the third. So once you get a handle on the coefficients from Pascal's triangle and the patterns with the variables, it's pretty easy to do this. And I wrote out more than I would have if I were just figuring it out on my own. You could multiply this quantity out by itself 3 times, and this is what you would get. But what if it was 4 times, or 5 times, or 8 times, or 9 times? You wouldn't want to keep multiplying it out. It would take forever. But following the pattern makes it a lot easier. Let's try one more. Let's expand x minus 2 over x to the fourth power. Okay, so what we're going to need to do is, first of all, figure out the coefficients from Pascal's triangle. Or maybe I'll do that second. Let's start off with the pattern here. So if I have a plus b to the fourth power, let's write out what the variables are. So I'm going to have a to the fourth, b to the 0, and then I'm going to have a to the third, b to the first, and then I'll have a to the second, b to the second, and then a to the first, b to the third, and finally a to the 0, which is 1, and b to the fourth. Now let me put the coefficients in front of there from Pascal's triangle. So for a plus b to the fourth, that would be this row here, 1, 4, 6, 4, 1. So 1, 4, 6, 4, 1. So 1, 4, 6, 4, 1. And then we're adding all these terms together. So here's the tricky part. We have to realize, what is A? Well, A is just X. So all the A's will get replaced with X. What's the B? Now here's where we have to be careful. Think of this as plus a negative 2 over X. So B is a negative 2 over X. So that's my A and that's my B. So let's work this out. So we have 1 times A to the 4th. So that's going to be, and I'll use parentheses even though you don't really need to for that, plus, and then we have 4. And then A is X, so X to the 3rd. And B is negative 2 over X. Notice we're going to get the X to cancel with one of the X to the 3rds. And then plus, then we have a 6. And then A we replace with X, and that's to the 2nd. B we replace with negative 2 over X, that's also to the 2nd. And then from Pascal's triangle we have a 4 times A, which is just X to the 1st power. You don't have to write the 1st power, obviously. And then B is negative 2 over X, and this is to the 3rd power. And finally, 1 times B to the 4th power, and B is negative 2 over X. Notice when I raise B to an even power, it's going to become positive. When I raise it to an odd power, it will be negative. All right, so let's start simplifying. So we're going to get 1x to the 4th. This is going to be a negative, and then 4 times 2 is 8, and we're going to have x cubed over x, which will simplify to an x squared. For the next term, we're going to have a plus, because a negative 2 over x squared, let me write that here, negative 2 over x squared is going to give us a positive 4 over x squared. And then I'm multiplying that times x squared and a 6. So the x squareds are actually going to cancel out completely, and we're just going to have plus 24. Now if you can do this work in your head, then that's fine. But if you're making mistakes, I would write out, or even over on the side somewhere, or just write an extra step. It's worth the time to save a mistake. Then we're going to have a negative, because negative 2 over x cubed is a negative. Now for this one, 2 to the 3rd power is 8, and then times 4. 8 times 4 is 32. Now we have an x to the 1st, but in the denominator we're going to have an x to the 3rd, so we can cancel, and we'll have an x to the 2nd left on the bottom. And then finally we're going to have a plus. 2 to the 4th power is 16, and then x to the 4th. And so that was a lot easier, I think, than multiplying everything out from the original expression, multiplying this out by itself 4 times. But this is what you would wind up with. Okay, the more you practice with this, the better you'll get at this. So for your assignment, I'd like you to go to page 19, section 1B. You're doing problem number 1, parts D, E, I, J, K, and L. For number 4, 4 has parts, I think, A, B, C, D, and then they have some Roman numerals within each part. So for number 4, I just want you to do problem C, part 5, Roman numeral V, 5. And then 6A, 8B, and 9A.